Some nights, when the world feels still and the air hums softly with silence, you might find yourself wondering, how did everything begin? How did the smallest pieces of existence, the atoms that make up you, me, the stars come to be from nothing at all? Close your eyes for a moment. Imagine the universe before time, before space, a quiet ocean of potential. No light, no sound, only the faint promise of something waiting to awaken. Then, in a single breath, the first spark, a pulse of energy expanding, stretching, unfolding like a heartbeat that never stopped. From that moment, every atom that would ever exist began its long, delicate dance toward being. Tonight, we'll drift through that story together, not through equations or cold data, but through wonder, through the soft rhythm of creation that still echoes in every breath you take. If this gentle voyage through science and starlight brings you peace, you can softly tap like or subscribe so that we may drift again through galaxies, questions, and dreams side by side. Now, let's close our eyes a little deeper and listen to how nothing became everything as we sink deeper into that quiet where everything first began. The vastness of creation folds inward until all that remains is a single atom floating in the dark. Within it, a tiny universe hums to itself, a bright center of energy. And around it, something even more delicate, an electron, forever in motion. It doesn't rest, and yet it never crashes inward. It drifts in perfect balance, tracing invisible paths that seem both fragile and eternal. For a moment, it feels almost alive, as though the same pulse that set galaxies in motion still beats here, in this smallest rhythm of existence. More than a century ago, this question stirred the curiosity of scientists who tried to give shape to the invisible. They pictured the atom like a miniature solar system, a bright nucleus in the middle, and electrons circling it like faithful planets. But this image, simple and beautiful, began to unravel. If those charged electrons truly orbited like planets, they would lose energy as they moved, radiating light until they spiraled inward and vanished into the nucleus. And yet, atoms endure. They have outlasted stars, storms, and time itself. Then came a quiet revolution. In 1913, a young physicist named Niels Bohr offered a vision that shimmered between logic and poetry. Electrons, he said, do not wander freely. They move in precise steps, fixed, quantized orbits, each with its own energy, its own rhythm. An electron can leap between these levels, but never drift in between. It was as if the universe itself had written music into matter, allowing only certain notes to play. Bohr's idea was born from an earlier spark, the insight of Max Planck, who discovered that energy comes in small, indivisible packets, not a continuous stream, but gentle pulses quanta like ripples of light through dark water. Bohr wove this idea into his model of the atom. Each orbit held a specific quantum of angular momentum, and the smallest orbit held exactly one Planck constant. Larger orbits carried 2, 3, or more, but never fractions, never halfway tones. With that, the atom was no longer a clockwork system, but a harmony waves encircling a center, folding perfectly into themselves. Picture a guitar string held at both ends. It cannot vibrate at random, only at certain lengths that create clear, resonant notes. The electron behaves the same way. Its wave wraps around the nucleus in patterns that fit perfectly. forming standing waves that define its distance and energy. Each orbit is a melody that holds the atom together. As quantum mechanics deepened, this image only grew richer. Electrons, it turned out, were both particles and waves flickering between two natures, like breath between inhale and exhale. They cannot fall closer to the nucleus than their lowest, most stable wave allows. Within that invisible boundary, they hum in delicate balance, drawn inward by electric attraction, yet held outward by their motion, their kinetic energy. This balance gives the atom its permanence. The pull of the nucleus and the push of the electron's motion cancel in a graceful symmetry. The total energy is negative, a quiet sign of stability. To free an electron, one must gift it energy, like a planet needing a final push to escape its sun. Until then, it remains bound, not trapped, but held in gentle equilibrium. So, the atom endures not by defiance, but by harmony. Its parts move within invisible rules, singing their quantized song across the fabric of existence. And somewhere, in that silent music of motion and light, lies the reason the universe holds together, and why it whispers softly, even in its smallest spaces. As we drift deeper into the origins of everything, the vast universe begins to unfold like a story whispered in the dark, a tale of how nothing became something. Every star that burns, every grain of dust, every heartbeat and dream, all are woven from atoms. These countless, invisible specks, far beyond numbering, are the universe's handwriting, repeating endlessly across time and space. Each atom carries a small trinity within: electrons, protons, and neutrons. Yet even these are not the beginning. Within them sleep smaller threads, quarks, the tiniest murmurs of matter. To trace their birth, we must travel backward, through silence and fire, to a moment when the universe itself was newborn. It began with the Big Bang, not an explosion, but an awakening, a pulse of energy so dense, so fierce, that space itself unfurled from it. In the very first instant, everything that would ever exist was compressed into a single, radiant point hotter and smaller than anything we can truly imagine. We call it a singularity, though even that word feels too certain, too human. For beyond that first flicker, our equations fall apart. What came before the beginning is still a secret the universe keeps. Our best guide, the standard model of cosmology, takes us as close as we can go to the first Planck time, a moment only 4,310, negative 43, 1043 seconds after everything began. Before that, time itself may not have meant anything at all. The four fundamental forces, gravity, electromagnetism, the weak force, and the strong force, were not yet separate. They moved as one, a single breath of creation. This era is known as the Planck epoch, a span so brief it feels more like a shimmer than a moment. Within it, all the laws of physics blur into unity. Gravity, normally the gentlest of the forces, becomes fierce and quantum, a storm of energy where space and time twist and dissolve. To truly see into that storm, we would need a theory that unites quantum mechanics and relativity, a dream physicists still chase like starlight on the horizon. Then, around 10,3,610, negative 36, 1036 seconds after that first shimmer, something extraordinary happens: cosmic inflation. The universe stretches, not through space, but as space itself. Faster than light, the fabric of reality balloons outward, expanding from something smaller than an atom to something the size of an orange. No explosion, no shockwave, just space growing from within itself. In that instant, the seeds of every galaxy, every world, were quietly sown. This inflation smoothed the wrinkles of the newborn cosmos, washing away the memory of what came before. By the time it slowed, around 10,310, -33, 1033 seconds, the universe was still unimaginably hot, a vast ocean of energy shimmering at temperatures beyond comprehension. But now, the stage was set for something new, the birth of particles. At about 10,1,210, -12, 1012 seconds, conditions began to resemble those recreated in our most powerful particle accelerators. Here, the universe's energy could condense into matter, photons, quarks, leptons, flickering in and out of existence in a wild equilibrium. Before this, we can only guess what might have been, perhaps ripples in a quantum field, or ghost-like inflaton particles decaying into matter. Whatever the true beginning, this was the dawn of substance, when energy learned how to take form. As the universe cooled to about 10,110, -11, 1011 seconds, and temperatures fell to roughly 1510, 1015 kelvins, the quark epoch began. The forces of nature started to diverge, the electroweak force splitting into two, the electromagnetic and weak nuclear forces. In that moment, the Higgs field awakened, spreading through the cosmos like a mist, giving mass to once weightless particles. From this quiet, symmetry-breaking came structure, the fundamental pieces of everything. Quarks, electrons, neutrinos began to endure. The universe was still a furious plasma, so hot that quarks could not yet settle into larger forms. But as time passed around 10,510, -5, 10.5 seconds after the beginning, temperatures dropped to about 1,000,000,000,000 kelvins. In that cooling, something miraculous occurred. Quarks bonded together, forming protons and neutrons, the first stable building blocks of atoms. The universe, still glowing with unimaginable light, began to hum with transformation. Mesons formed and vanished. Photons streamed freely for the first time. Everywhere, pairs of particles and antiparticles met and destroyed each other, releasing bursts of radiant energy. Yet within this perfect symmetry, there was the slightest imbalance, a tiny excess of matter over antimatter, perhaps one extra particle in every billion. It was a delicate imperfection, but it was enough. That small asymmetry became everything, the reason there is something instead of nothing. Because of it, a few protons and electrons survived the great annihilation, carrying forward the promise of worlds to come. And so, from the silence after that fire, the universe began to cool, to expand, to breathe. Its fabric still shimmered with the memory of creation, and scattered across that vastness were the first ingredients of all matter, waiting, patient, and eternal, to one day become the atoms that form stars, oceans, and the gentle pulse of life. The first atoms were not yet born, not quite, but their song had begun. It played softly through the darkness, a rhythm of balance, expansion, and light. The universe was only seconds old, and already dreaming of shape. In the great symphony of creation, the universe continues its dance, particles swirling, colliding, dissolving, and reforming in a cosmic rhythm too vast for sound, yet somehow deeply familiar. Each force Each flicker of temperature moves like a note in an infinite composition, shaping the structure of everything to come. By the time a single second has passed since the beginning, the Lepton epoch arrives. The universe has cooled to about 5 billion kelvins, still unimaginably hot, but calm enough for a new balance to emerge. Matter and antimatter continue their delicate duel, canceling each other out in flashes of light. Yet, because of that ancient asymmetry, that faint, precious imbalance, a small number of protons, neutrons, and electrons remain. These survivors are the seeds of all matter, carrying forward the universe's quiet intent to become. A few minutes later, as the cosmos expands and cools further, the era of Big Bang nucleosynthesis begins. Within this brief but monumental window, the first atomic nuclei take shape. Protons and neutrons, bound together by the strong nuclear force, begin to form the lightest elements: hydrogen, helium, and traces of lithium. It is a fleeting alchemy, born from both order and chaos. The newborn universe settles into a simple recipe: about 75% hydrogen, 25% helium, and only a whisper of anything heavier. The rest, the carbon of life, the oxygen of breath, the iron of worlds, will have to wait for the hearts of stars. But in this moment, the foundations of matter are laid. Still, atoms are not yet whole. The universe remains a glowing ocean of charged particles, a fog of energy where light cannot travel freely. Photons, the messengers of illumination, constantly collide with electrons and ions, scattering endlessly. This era, the photon epoch, stretches on for hundreds of thousands of years. The cosmos is bright, but blind, full of light that cannot escape. Only when the temperature finally falls to around 3,000 kelvins does the mist begin to clear. Electrons, now cooled and slowed, drift close enough to protons to be captured by their pull. They join together in the first act of cosmic bonding, creating neutral atoms in a process called recombination. And in that instant, everything changes. For the first time, light is free. The photons, no longer trapped in their endless scattering, begin their long, unbroken journey through space. A journey that is never truly stopped. That light still surrounds us today. It is stretched and cooled across billions of years, softening into the faint glow we call the cosmic microwave background, the oldest light in existence. When we look at it, we are seeing the universe as it was when it first became transparent, when atoms were born and the darkness began to lift. It is the first whisper of the cosmos, a silent, golden afterglow left behind by creation itself, carrying across eternity the memory of how matter found its form and how light first learned to shine. As we drift through the great cosmic story, another quiet wonder rises, a question that feels both simple and infinite. Do atoms ever truly touch each other? It's a thought that turns familiar sensations into mysteries. When your fingertips brush against a surface, when a cup rests on a table, when one star's light crosses another's path, what does touch truly mean in a universe made of emptiness and charge? In our everyday world, touch feels tangible, undeniable. You press your palm to the wall, and there it is, solid, certain. When two magnets draw together, or when a charged balloon clings softly to your sleeve, you can feel the invisible pull of their forces. But that feeling, that contact, is not the meeting of matter with matter. It is the dance of invisible fields. Magnets don't touch, their energy does. Balloons don't meet, their charged surfaces reach out through space. Every interaction we perceive, from the push of a magnet to the firmness of the ground beneath our feet is the quiet language of electromagnetic forces. It's not solidity, it's intimacy at a distance. Now imagine shrinking smaller and smaller until the whole world dissolves into motion. At the scale of atoms, everything is alive, vibrating, colliding, spinning. There are no sharp edges here, no solid borders. Each atom is mostly empty space, with a tiny, dense nucleus at its core and a cloud of electrons that hums around it like soft mist. These electrons are not tiny marbles circling the nucleus, but waves of probability shimmering regions where the electron might be, never exactly pinned down. So when two atoms touch, what truly happens is that their clouds meet not as surfaces, but as influences. Their electrons begin to repel one another, forming an invisible cushion that keeps them from collapsing together. The feeling of resistance you sense when you press against something is that cushion, the electromagnetic field saying, "This far, no closer." That's why your coffee cup doesn't fall through the table. The atoms of the cup and the atoms of the table never physically meet. They simply hold each other in balance, their electrons pushing back just enough to resist gravity. Touch, then, is not contact, it's connection, a shared tension between forces, a dance of nearness without merging. And yet, sometimes atoms do more than repel. When they draw close enough and their energies align, a gentler force begins to whisper the van der Waals force, a subtle part of the same electromagnetic field. In that delicate moment, attraction overcomes repulsion, and atoms begin to bond. They form molecules, new entities, born from their union. Within these bonds, their electron clouds overlap, weaving together the structure of matter, air, water, life. In that sense, atoms do touch, not by colliding, but by sharing. At even greater extremes, within the hearts of stars, touch takes on an entirely different meaning. Here, under immense pressure and heat, atoms are forced so close that their nuclei, usually held apart by the fierce repulsion of their positive charges, finally merge. This is nuclear fusion, the ultimate intimacy of matter. Two atomic hearts unite to become one, releasing a burst of radiant energy, the same light that warms our world and illuminates the night sky. So, do atoms ever truly touch? Not in the way our senses imagine, but in every moment through repulsion, attraction, balance, and fusion. They are in constant conversation. The solid world you feel is not made of things pressing together, but of fields weaving through space, holding one another in delicate equilibrium. Touch, it turns out, is not a meeting of matter. It's the quiet recognition of one atom by another, a cosmic closeness that binds the universe together, from your fingertips to the fires of the stars. As we drift deeper into the quiet logic of the cosmos, another question unfolds, one that glimmers with both simplicity and mystery. Are two atoms of the same element ever truly identical? At first, it feels obvious to say yes. A gold atom is a gold atom, a carbon atom, a carbon atom. But when we listen more closely, when we peer into the gentle rhythm of the atomic world, sameness begins to dissolve. Each atom carries its own subtle variations, its own fleeting moods, shaped by energy, motion, and time. Start with the electrons, the shimmering veil that surrounds every nucleus. These electrons do not stay still. They leap between energy levels, like notes in a melody. One copper atom might hold an excited electron, glowing softly as it releases light on its way back down. Another, calm and grounded, remains ones dark and quiet. Though they share the same name, copper, their behaviors differ, their songs slightly out of tune with each other. Chemists know this well. To understand how atoms will react, one must know not only what they are, but how they feel, their charge, their energy, their spin. An iron atom in stillness behaves differently from one trembling with motion. When cooled and slow, atoms link arms easily, forming solid bonds. But when heated, their motion becomes restless, and those same atoms slip past each other, turning solid into liquid. Even among identical elements, movement alone can rewrite the rules of connection. And then there is the nucleus, the dense, beating heart of the atom. Within it, protons and neutrons weave tightly together, yet they too can vibrate, rotate, and shift into higher energy states. Two gold atoms may have identical electron clouds, but if their nuclei pulse at different frequencies, they are no longer truly twins. One may respond differently in a nuclear reaction, or release a faint trace of energy that the other does not. There is also a quieter distinction that hides even deeper: the number of neutrons inside the nucleus. Some atoms of the same element carry extra ones, heavier and slightly unstable. These variants are known as isotopes. A carbon 1,2 atom and a carbon 1,4 atom are both carbon, yet their fates diverge with time. Carbon 1,2 remains stable and silent, while carbon 1,4 slowly transforms, its nucleus shedding energy in tiny, predictable breaths. That slow transformation, radioactive decay, is how we measure the ages of ancient bones and forgotten forests, counting the rhythm of atoms as if listening to time itself. So even when two atoms share the same electrons, the same protons, and the same chemical soul, their inner lives can differ. Their nuclei might quiver in different ways. Their particles might spin just a little faster or slower. Their histories might carry different scars from the stars that forged them. And yet, in another sense, identity itself begins to blur in the quantum world. If two carbon atoms truly match in every possible state, every energy level, every vibration, every spin, then they are indistinguishable. In the realm of quantum physics, sameness becomes absolute. Two such atoms are not merely alike. They are the same in essence, interchangeable, and without memory of origin. So, do identical atoms exist? Not in the way our minds expect. Each atom hums with tiny variations, shifting with motion, energy, and time, unique for a moment, then fading back into the great harmony of matter. But when all differences vanish, when every quantum state aligns, individuality itself disappears. In that deep, silent symmetry, atoms remind us of something timeless, that even in a universe made of countless distinct forms, all things are, at their core, one waves in the same endless sea of being. As we journey through the quiet architecture of matter, another gentle question flickers to life. If atoms are the building blocks of everything we see, do they have color too? After all, the world around us is a canvas of color: the blue glow of a screen, the soft hue of skin, the crimson whisper of sunset. And yet, beneath all that beauty, everything is made of atoms. So, do these tiny builders carry the colors they create? The answer drifts between perception and physics. Color, as we know it, isn't truly out there. It's something our minds paint onto light. What we call red, blue, or gold are not properties of things themselves, but the way our brains interpret light waves that reach our eyes. The universe, in truth, is silent, filled not with color, but with energy, Light itself is made of photons, tiny packets of energy that behave both as particles and waves. This strange dual nature, called wave-particle duality, means that light can spread like a ripple through space, yet arrive as a single quantum of energy. These waves come in many frequencies, stretching from enormous radio waves as wide as worlds, down to gamma rays smaller than atoms. Our eyes can see only a narrow band of this grand spectrum, what we call visible light. Long ago, this range was chosen not by design, but by the quiet logic of evolution. The first living eyes opened underwater, where only certain wavelengths could pass through. The light that could glide cleanly through water, roughly from violet to red, became the palette of life. Had we evolved beneath the light of another star, or in a sea of methane or sulfur, our sense of color might have been entirely different. But how does light form, and how does it become color? Deep in the sun's heart, hydrogen atoms fuse into helium under immense pressure, releasing blinding bursts of energy in the form of gamma rays. Those photons bounce and scatter for thousands of years inside the sun, losing energy as they go until finally escaping as the warm, golden light that reaches Earth. When that light touches matter, its fate depends on what it meets. Some materials absorb light, taking in certain wavelengths and turning them into heat. Others reflect light, sending parts of it back into the world. A blue shirt, for example, looks blue because it reflects blue wavelengths and absorbs the rest. Black absorbs nearly everything, which is why it grows hot beneath the sun, while white reflects nearly all, staying cool and bright. But color is not just about reflection, it's about arrangement, how atoms gather, how molecules form patterns. Snow and ice are made of the same water molecules, yet snow looks white and ice looks clear. Why? Because their atomic structures scatter light in different ways. Even the most ordinary sight, sunlight glinting off a frozen window, is a performance of countless atomic arrangements playing with light. Now, if we return to the heart of the question, does a single atom have color? The answer, softly, is no. The wavelength of visible light is thousands of times larger than an atom. A single atom is too small to scatter or reflect light in a way we can see. It lives beneath the scale of color itself. And yet, atoms do give birth to light in other ways. When they're heated, their electrons grow restless and leap to higher energy states. As they fall back down, they release photons, tiny sparks of color. This is what happens when a flame glows red, orange, or blue. But here too, color arises not from a single atom, but from many atoms acting together, each releasing its photon into the collective glow. In a laboratory, when electricity flows through a gas, the atoms within it light up each element, singing its own unique frequency of light. Hydrogen glows pale pink, helium shines gold, neon blazes red-orange. These colors form the emission spectrum, a fingerprint so distinct that astronomers use it to identify elements in distant stars. So, while an atom itself has no visible color, its energy, its dance of electrons, gives rise to all the colors we know. The reds of sunset, the green shimmer of leaves, the blue of your screen, all are the echoes of atoms interacting with light. The next time you look at something beautiful, remember, beneath the surface, color does not exist, only light, motion, and the quiet conversation between atoms and your eyes. The universe paints, and we perceive together, creating the illusion of color where none truly is. Settle in, breathe in, and out. Now let's slip beneath the skin of matter, into the warm hush where the nucleus lives, a tiny hearth of charge and motion. There, side by side, sit protons, each carrying the same positive sign, each, by every everyday instinct, wanting to push the other away, according to the simple tug of electromagnetism. They should explode apart, and yet the nucleus endures. Why? The universe answers with 4 quiet rules, its fundamental forces. Gravity is the slow drum we hear on the largest stages. Stars, galaxies, tides. The weak force reshapes particles from within, letting suns burn and elements transmute. Electromagnetism is the nimble thread that binds light to matter, drawing electrons toward protons and composing chemistry's songs. And deeper still, where distances shrink to the width of a proton, there is a fierce whisper, the strong nuclear force. It is the hand that holds the nucleus together, a grip so intense that at nuclear scales, it easily overrules electromagnetic repulsion. If electromagnetism were a shout, the strong force would be a clasped hand at your wrist, steady, decisive, roughly 100 times stronger than electromagnetism at the radius of a proton. It acts only where closeness is extreme, fading quickly with distance. That short reach is a blessing. It keeps nuclei compact and prevents matter from crushing itself under an overwhelming attraction. To understand how this works, we must open the proton and the neutron and step inside. They are not smooth, solid beads. They are storms, quarks racing in tight orbits, lashed together by gluons, the carriers of the strong force. 3 quarks, 2 up and 1 down, braid a proton. 2 down and 1 up weave a neutron. Gluons knit them, trading a special kind of charge called color. Not the colors of sight, but a bookkeeping of the strong force. Red, green, and blue combining to white or neutral. Quarks tug on one another so forcefully that trying to pull them apart tightens the bond, like stretching a rubber band whose tension grows with distance. Keep pulling, and you don't free a quark. You summon new pairs from the vacuum. A quark, an antiquark, snapping into existence to keep every piece confined. This is confinement. The strong forces vow that quarks will never wander alone inside a single proton or neutron within a nucleon. This web of gluons is everything. But between nucleons, from one proton to the next, that inner storm leaks a residue, the way the scent of a flower reaches beyond its petals. That leftover attraction is the nuclear force you feel at the scale of the entire nucleus. It is often pictured as an exchange of mesons, quark-antiquark pairs, especially pions. One nucleon tosses a meson to another, and the toss itself tugs them closer. The result is a force with a sweet spot, immensely strong when nucleons nearly touch, then fading sharply beyond a couple of femtometers. A femtometer is a millionth of a billionth of a meter. Because it dies off so quickly, there's a practical limit to how many protons and neutrons can crowd together and still be stable. Make the nucleus too large, and the long-range repulsion of all those positive charges begins to win. Instability grows, and the nucleus seeks gentler arrangements through alpha decay, beta decay, or fission. The periodic table's upper reaches are a careful truce between attraction and pushback. All of this fierce binding does more than hold things together, it gives matter mass. Most of the mass of the world around you is not the quiet rest mass of the quarks themselves, nor a direct gift from the Higgs field, but the kinetic and field energy of quarks and gluons trapped in their tiny arena. The weight of a proton is largely the energy of motion and the energy of the strong forces binding, humming and folded tight by E equals mc squared. In a very real sense, you are made of stored motion. Because the nucleus is a living storm and not a marble, even measuring its size is an art. For decades, physicists estimated the proton radius, the extent of its positive charge, using two kinds of delicate listening. One method is scattering. Fire electrons at hydrogen, a single electron bound to a single proton, and watch how their paths deflect. The pattern reveals where the proton's influence begins to fade, hinting at its boundary. The other method is spectroscopy. Measure the exact energies an electron needs to jump between levels in hydrogen. An electron spends a sliver of time inside the proton's charge cloud. If the proton is a touch larger, the electron slips in more. The attraction weakens slightly, and the required jump changes. From such tiny shifts, a radius emerges. For years, the numbers from these two listens agreed on roughly 0.876 femtometers until 2010, when a new voice entered the conversation: muonic hydrogen. Replace hydrogen's electron with a muon, a heavier cousin, about 207 times the mass, and suddenly the electron, now a muon, orbits closer, lingering far more in the proton's electric embrace. That closeness makes the energy levels exquisitely sensitive to the proton's size. The result? A measured radius near 0.84 femtometers, about 4% smaller than expected. The room went quiet. Had we missed something? Was there new physics peeking through the keyhole? Years of careful work followed. New electron scattering techniques, refined spectroscopy, and fresh measurements with ordinary hydrogen returned values clustering around the smaller number. In 2019, precision spectroscopy in electronic hydrogen again pointed to a radius near 0.833 FM, harmonizing with the muonic result. The consensus settled. The proton is smaller than we thought, and the earlier discrepancy was likely in our methods, not a crack in the foundations. Even so, the episode was a gift, a reminder that matter is subtler than our metaphors, and that nature always has another layer of nuance to reveal. Let's step back now and ask a more tactile question. If atoms are mostly empty space, a tiny nucleus surrounded by a wide, whispering cloud of electrons, why doesn't your hand pass through a table? Why doesn't light thread easily between those gaps? Begin with light. When a photon approaches matter, it meets electrons that are arranged in quantum patterns, standing waves described by Schrödinger's equation. Think of a grand hall filled with dancers, each set to a particular step, a particular rhythm. An electron can only occupy one pattern at a time, and within an atom, no two electrons share the exact same step. Pauli's exclusion principle. If incoming light carries exactly the right energy, an electron can absorb it and change its dance, jumping to a higher, more energetic pattern. If not, the light may be reflected, scattered, or pass through. The colors you see, the shine of metal, the glow of glass, all are the visible consequences of which steps are allowed, which are filled, and how tightly the electrons are held. As for solidity, the sensation in your fingertips, it is not because matter's surfaces literally meet, but because their fields and quantum rules refuse to overlap. Bring the electrons of your finger close to the electrons of the table, and two barriers surge up at once. First, there is electrostatic repulsion. Negative charges resist sharing the same space. Second, and more profoundly, there is the exclusion principle again. Electrons are fermions, and their total quantum state must be antisymmetric. When two sets of electron clouds are pressed together, many electrons would be forced into quantum steps already taken. They cannot. To avoid forbidden duplication, they must be promoted into higher, emptier states. A rearrangement that requires energy. You supply that energy with your push, and the material pushes back. The result is a force that feels like a surface. Your finger never really touches the table. Their fields meet, and the shared quantum bookkeeping says no farther. This same story explains why light doesn't drift freely through empty atoms on its way through a solid. The electronic patterns in the material, stacked and broadened into bands when atoms sit side by side, decide which energies can pass, which are swallowed, which are reflected. In metals, electrons roam more freely, and light is reflected like a returned echo. In glass, allowed steps line up so that visible photons mostly pass through. In dark, absorbing materials, many photons are eaten, their energy converted to vibration and warmth, what we call opacity or transparency. Mirror or matte is the signature of a community of atoms agreeing on how their electrons may dance together. But what of the nucleus itself? Can it ever be made to touch another? In the sun's heart and in the hot breath of newborn stars, the answer is yes. There, heat and pressure crowd nuclei so close that their outer electron clouds are stripped away, and their Coulomb walls, the electrostatic fences, are squeezed thin. Quantum mechanics adds one more grace: tunneling. Even if the classical hill is too high, a nucleus has a small chance to simply appear on the other side, as if uncertainty itself kept a secret door. When that happens, and two light nuclei draw close enough, the strong force seizes them, welding them into a larger nucleus in an act of fusion. If the products are lighter than iron, the binding energy released exceeds the cost of the climb, and light pours out. This is how stars shine, by overcoming repulsion to tap the deeper well of the strong force's embrace. Notice the symmetry in these tales. On one scale, the strong force keeps quarks bound so tightly that they create protons and neutrons and lend us mass. On the next, a softened residue of that strength binds nucleons into nuclei, but only to a point. Beyond a few femtometers, the strong hand opens, and electromagnetism's gentle push returns. A nucleus is thus a negotiation, not a siege, and matter as a whole is a parliament of refusals and allowances. Electrons refusing to share steps, fields refusing to overlap, photons allowed or denied by the spacing of quantum rungs. If you like, imagine your body for a moment as a cathedral of these small agreements. Protons and neutrons in your bones are held by gluon storms. Electrons in your nerves hold to their paths by quiet rules. Atoms link into molecules by sharing electron songs. Molecules fold and clasp and unlace again. At every level, not flying apart is not an accident, but the signature of forces tuned just so. The strong force, strong enough but short-armed. Electromagnetism, long-reaching but balanced by quantum law. The weak force, gentle, yet able to change identities when the cosmos asks. Gravity soft, yet inexorable, gathering stars where fusion can begin, and inside the proton, where our story began. The smallness itself is a kind of solace. A radius of roughly 0.84 femtometers, smaller than we first believed, reminds us that even our finest rulers must be recalibrated by listening more carefully to nature's music. The proton is not a place with walls. It's a harmony of motion and field, crowded into the smallest room. Its mass, a memory of energy trapped and turning. It does not let its brothers flee, because the strong force will not let go. It does not swallow them, because the strong force's reach is brief and merciful. So the nucleus holds, the table resists your touch. Light stops at your skin and warms it, or passes through your window and paints your room. Behind each ordinary sensation is this layered ballet quarks, confined, mesons exchanged, electrons arranging themselves so that no two dance the same step, photons asking permission to pass. What feels solid to your fingers is really a pageant of no farther and not this way, answered softly but firmly by the laws of the small. Let that be a comfort as you breathe. The universe is not a chaos of collisions, but a choreography of constraints. Protons do not fly apart because a deeper promise holds them. Your hand does not fall through the table because countless electrons keep faith with ancient rules. In that steady keeping, you and everything you touch remain whole, a quiet proof, written in the tiniest script, that order lives at the heart of things. Slip a little closer to the quiet where matter makes up its mind. Out in the open, the universe seems sparse. Fewer than 100 naturally occurring elements scattered through stars, stone, water, and breath. And yet from this small alphabet, an immeasurable library appears. Scents and salts, sugars and skies, the proteins of life and the dust of comets. The secret is that atoms rarely travel alone. They prefer company. They bind, they share, they trade, and in doing so they become molecules, the true characters of chemistry's story. You meet them every moment. The oxygen you breathe arrives not as single atoms, but as O2, two oxygen atoms clasped together. Most of the air is N2, nitrogen in pairs. Water is H2O, a gentle triangle of two hydrogens and one oxygen. Even where you expect simplicity, you find community. The world's diversity is a chorus, sung by atoms in company rather than in solitude. Why do they join? Because nature drifts downhill. Like a marble perched on a ridge, a system slides toward lower energy if it finds a path. Molecule formation is that path. When atoms arrange themselves so the total energy of the pair is lower than the sum of their separate energies, the universe nods. Yes, the bond forms, and the pair becomes more than what it was. Hydrogen is the cleanest place to watch this happen. One proton, one electron, the simplest atom. Bring two hydrogens near. At first, they only feel each other's presence, a faint shiver of attraction and repulsion. Electrons, both negatively charged, do not love crowding. They push back, but each electron also feels the pull of the other atom's proton, and that pull is inviting. As distance shrinks, these contrary urges negotiate. Too far apart, and the attraction is weak. Too close, and repulsion swells. Between those extremes there is a sweet spot, a particular separation where the push and pull cancel into comfort. At that distance, the pair's total energy dips, and the hydrogen atoms become H2. If you could draw this courtship, you would sketch energy on the vertical axis and distance on the horizontal. The curve falls into a valley, bottoms out, then rises steeply, a basin with a single resting place. That resting place is the bond length. The depth of the basin is the bond energy. Leave the atoms alone, and they settle there, vibrating gently like a pendulum at the bottom of its swing. Nudge them, and they hum. Pull them too far, and the partnership snaps. In the language of quantum mechanics, the whole scene is contained inside a single symbol, the Hamiltonian, an operator that tallies all the moving parts, the kinetic swiftness of electrons and nuclei, the electric attractions between electrons and protons, the repulsions of like charges. The Hamiltonian sits at the heart of the time-independent Schrödinger equation, the rule book that says which waves, which electron arrangements are allowed. Solve it exactly for two atoms, and you own the secret of their bond. We often cannot solve it perfectly, but we can see what it says. There exists a shared state, lower in energy than the separate states, and that is why atoms clasp hands. When that hand clasp is a sharing of electrons, we call it a covalent bond. The electron cloud of one atom overlaps with that of its neighbor, so that the electrons can belong to both at once, spending time where their presence lowers the total energy of the pair. The picture is not two beads glued together, but two waves interweaving, their combined shape smoother and quieter than either on its own. Underneath this sharing lies a strict rule with a gentle consequence, the Pauli exclusion principle. Electrons are fermions. No two can occupy the same quantum state within an atom. This rule stacks electrons into shells and subshells, filling the lowest seats first. Certain totals 2, 10, 18, 36, 54, 86. Complete layers, so neatly that atoms with these counts, the noble gases, are content to stay as they are, rarely reaching for partners. Other atoms sit just one or two electrons, shy of such calm, or with one or two loosely held extras. They are restless. They seek peace by sharing or trading. Thus, chemistry's two broad roads appear. On one road, atoms share electrons, covalent bonds, shaping molecules like O2, N2, and H2O. On the other road, atoms transfer electrons. One gives, one takes, and opposite charges attract in an ionic bond. In both cases, the destination is the same: a lower total energy, a fuller, quieter electronic arrangement that feels like rest. Return for a moment to our picture of the energy valley. For real molecules, that valley is not perfectly parabolic. It is slightly asymmetric, steeper if you compress the bond, gentler if you stretch it. A simple mathematical sketch that captures this shape is the Morse potential. It tells you where the valley's floor lies, the equilibrium bond length, and how deep it is, the dissociation energy. Though it is only an approximation, it sings the right melody. Bonds are springs that soften as they stretch, then break. The same logic of comfort at lower energy scales upward from pairs to trios and beyond. Take water. Two hydrogens share with oxygen, but the sharing is uneven. Oxygen draws the shared electrons a little closer. This slight imbalance leaves water with a tender separation of charge, a dipole, making water molecules attract one another in quiet chains and clusters. From this, 1,000 wonders flow. Surface tension, the way ice floats, water's power to dissolve salts, the slow heartbeat of climate. All of it is the choreography of electrons, finding arrangements that cost less energy than loneliness. Even the elements that seem aloof, the noble gases with their filled shells will, under the right conditions, feel a whisper of attraction. Electron clouds can momentarily slosh to one side, creating fleeting dipoles that tug on neighbors. van der Waals attractions. They are weak and short-lived, yet they matter. They help geckos climb windows, guide the folding of proteins, and contribute to the subtle stickiness of condensed matter. They remind us that bonding is a spectrum, not a switch. Physics keeps the score. Every proposal a set of atoms makes, shall we share here or there? Shall we trade one electron or two? Shall we align spins this way or that? Is judged by the Hamiltonian, with Schrödinger's equation handing down the allowed states. Pauli ensures crowding is forbidden. The result is not a lecture, but a landscape. Valleys where molecules rest, ridges they rarely cross, and passes where reactions can proceed when heat or light lends a push. Those magic numbers of stability are not magic at all, but the arithmetic of waves in confined spaces. Electrons in atoms are standing waves, and only certain shapes fill a shell, and the next electron must start a new shape at a higher energy. Atoms that sit just before or after these comfortable counts are the most eager dancers in chemistry's hall halogens, reaching to take one more electron. Alkali metals, happy to offer one away. What we call reactivity is the distance to comfort. What we call bonding is the path down. In practice, for many atom systems, the exact calculation becomes an ocean. We turn to approximations. Born Oppenheimer, separation, to treat heavy nuclei as slow and electrons as swift. Morse-like curves to model bonds, computational methods to search for valleys in vast landscapes. The details are intricate, but the melody never changes. Molecules form because the whole is quieter than the parts, and yet a gentle boundary remains. Quantum mechanics tells us how bonds arise, which shapes of electron clouds are allowed, which exchanges lower energy, which symmetries are permitted. It gives us astonishing predictive power. The length of a bond, the angle of a molecule, the heat released when a pair becomes a whole. But the deeper why the universe is written in waves and quanta at all, is a question that slips through our fingers like water. Perhaps that is fitting for a bedtime thought. We are children of a logic we can follow, but not fully explain. So let the image linger. Atoms as small musicians, each with a limited scale to play. Molecules as chords, whose notes, sounding together, resolve attention. The air around you, O2 and N2, is a woven harmony. The water beside your bed, a triangle of shared notes. Everywhere, the universe rolls downhill toward rest, and in that descent, it makes beauty. Bonds that hold, shapes that fit, patterns that last. Molecules are simply atoms choosing again and again. The comfort of company. Drift with me to a place where matter forgets its ordinary shape. Out there, in the dark after a star's last breath, a remnant can shrink until the familiar scaffolding of atoms collapses. What remains is a neutron star, a city-sized sphere, roughly 10 kilometers across, holding more mass than the Sunday. To the quiet mind, it feels like a single, colossal nucleus. But is it, truly? A living star survives by balance. Gravity pulls inward. Fusion pushes back. Hydrogen fuses to helium. In heavier stars, helium to carbon, then to neon, oxygen, silicon, until the chain reaches iron, where fusion no longer pays its energy debt. Pressure falters. Gravity, patient until now, tightens its grip. The stellar core plummets inward at astonishing speeds, the outer layers chasing it like thunder. In that crush, electrons are driven into protons. Inverse beta decay. turning them into neutrons and releasing ghost-like neutrinos that race away. The electromagnetic scaffolding of ordinary atoms, electrons, bound to nuclei, gives way, and matter is squeezed to nuclear density. What stops the fall is not a wall, but a rule: degeneracy pressure. Neutrons are fermions. They refuse to share the same quantum state. Pack them tightly enough, and this refusal becomes a force. Add to it the short-range repulsion of the strong interaction at near nuclear separations, and a new balance appears. Gravity presses. Quantum and nuclear physics press back. The result is a star that weighs like a sun, yet rests on a radius the size of a town, a quiet, impossible jewel. If we could peel it layer by layer, we'd find that a neutron star is not a single smooth nucleus, but a stratified world. In the crust, atomic nuclei still exist, locked in a rigid lattice, bathed in a sea of electrons. Deeper down, pressure soars and neutrons drip out of nuclei, pooling like a superfluid mist between ions. Deeper still, in the core, neutrons dominate, with a sprinkling of protons and electrons, and perhaps muon, many of them forming superfluid and superconducting phases, matter flowing without friction, magnetic fields threading through in quantized strands. Whether stranger species lurk at the very center hyperons, quark matter remains an open lullaby of questions. So a neutron star is nucleus-like in density and binding, but not a giant, single atom. It is a layered symphony held together by gravity and the strong force, not by electron shells. How could such a thing exist at all? Because nature's forces are tuned to allow it. At nuclear distances, the strong force binds, and at astronomical distances, gravity gathers. Between them, matter can be crushed past chemistry into a new state that still resists total collapse. Yet this exotic endurance is only part of a larger, older story, one written in the first seconds of the universe. In the newborn cosmos, as temperatures fell and reactions slowed, protons and neutrons froze out of equilibrium. A small, crucial asymmetry took root because of a subtler tuning. The down quark is a bit heavier than the up quark. Neutrons, 2 downs plus 1 up, therefore weigh slightly more than protons, 2 ups plus 1 down. As the universe cooled, reactions that turned neutrons into protons were just a little more favored than the reverse. The outcome was a lasting imbalance, roughly 7 protons for every neutron. That gentle tilt shaped everything. With protons in the lead, hydrogen became abundant. Hydrogen lit the first stars. Stars forged helium and the heavier elements. Chemistry unfolded. Life became thinkable. Had the masses been reversed, had neutrons been lighter, neutrons would have dominated. Hydrogen would have been scarce and fragile, and the universe might have slumped into a cold, dim hush with little chemistry to speak of. No long-burning stars, no warm shores of possibility. We live in a cosmos where protons win just enough for stars to ignite, and where, at their endings, gravity can still squeeze matter past the electron shell world into neutron-rich suns. Seen in this light, a neutron star is both a consequence and a counterpoint. It is born from ordinary stellar fuel, hydrogen and helium, whose abundance depended on that early proton favor. Yet the star's death erases the very chemistry that once sustained it, stripping away electrons and silencing the periodic table. What remains is matter at its simplest complicated state, neutrons in crowded agreement, their quantum refusals adding up to a kind of strength. So, is a neutron star a colossal atom? Not quite. An atom is a nucleus wearing an electron cloud. A neutron star is gravity wearing a nucleus. One is held together by electromagnetism, the other by the strong force and the weight of space-time itself. And yet the metaphor is tenderly true in spirit. Both are places where rules make refuge, where balance is born from opposing urges, where the tiniest and the grandest obey the same quiet mathematics. Breathe with that for a moment. The same small difference in quark masses that favored protons, that fed the fires of stars, also permits the existence of their gravest remnants. From hydrogen's first spark to a neutron star's dark glow, the universe hums one continuous note, a balance that lets matter gather, burn, collapse, and endure. And in that balance, we find not only how things are, but why there is a night sky at all, and a mind to wonder beneath it. There is another tilt in the cosmos, quiet, decisive, that made room for everything we know. In the early seconds after the beginning, matter and antimatter were born together like mirror sparks. By every simple rule, they should have met and vanished in perfect balance, leaving only light, and yet a whisper of difference remained. Just a few extra grains of matter for every billion pairs. That small surplus is why stars exist, why atoms endure, why there is anything left to tell a story at all. To feel the weight of that imbalance, imagine a darker tale from a distant sky. Picture a world not unlike our own, clever and quarrelsome, where the climb from sticks to circuits never learned to slow. Their engineers find a way to make antimatter, to trap it in electromagnetic bottles, not in tanks or shells, but in fields that keep the mirror particles from touching the walls. They do not need detonators or drums of fuel. Antimatter is its own fuse. When a gram meets a gram of ordinary matter, both unmake themselves, releasing a flood of energy with a terrible clinical completeness. A single gram carries the fury of a city-ending weapon. One accident, one miscalculation day collapses into night. The air itself becomes fire. The world's map is redrawn by a burst that leaves no ashes to measure. This is what perfect symmetry would have meant for us, written large across a planet. Matter and antimatter cancel. Where they meet, they leave only radiation and absence. And yet, we are still here. The universe's earliest arithmetic stumbled, mercifully, just enough to leave residue, the matter that seeded galaxies, oceans, and breath. We live among tiny traces of antimatter even now, born in lightning, in cosmic rays, in the patient decays inside rocks and living bodies. But they are flickers against the overwhelming tide of matter. The great asymmetry holds. Let's step gently into a broader speculation the mind sometimes craves at night. What if our universe is as small to some larger order as an atom is to us? The observable cosmos feels limitless, and yet it is only a luminous bubble, perhaps a fraction of a vaster whole that we cannot see. Theories with many faces, inflationary landscapes, eternal inflation, branching quantum worlds suggest a multiverse, a quilt of regions with different arrangements of fields and constants, some friendly to chemistry, some sterile and dark. In such a picture, what we call an electron or a proton here might be like notes in a greater composition. Our laws might be local grammar rather than universal law. There's an older, more playful thought, the one electron universe. Perhaps all electrons are the same because they are, in fact, the same electron, tracing back and forth through time, leaving multiple footprints that we read as multitudes. It is not a theory we lean on to make predictions. It is a parable about identity in the quantum world, where particles of the same kind are truly indistinguishable, where history is a haze and only the pattern matters. Still, as a bedtime lantern, it throws a warm light. Sameness and multiplicity are not as far apart as they seem. Fiction has long wandered these corridors, universes in a grain of sand, cities inside a snowflake, a cosmos nested in a marble. Science, more careful, asks only that we keep the question open. Is our sky an interior? Could our everything be a small chamber in a larger architecture? Without a theory of everything, a calm union of quantum mechanics with gravity, we cannot say. For now, we hold two powerful books at once: the quantum rules that govern the small and the smooth geometry that shapes space-time. We read from one, then the other, and the seam between them is where our wonder pools. Even so, it helps to be precise about beginnings. We sometimes say the universe came from a singularity, an infinitely dense point. What we really mean is that when we press our known equations back to the first instance, they stop making sense and point to a limit they cannot cross. Whatever the true starting state was, it contained the capacity for the parts of atoms, the fields, and symmetries that would later bloom into quarks and electrons, protons, and light. It was not an atom, but a promise. Conditions from which atoms could eventually arise. Return, now, to the asymmetry that spared us from emptiness. No one yet holds the full recipe of baryogenesis, how that tiny excess of matter emerged, but we know some ingredients it must have contained. Processes that treat matter and antimatter a little differently, reactions that occur out of equilibrium, and changes in symmetries as the universe cools. However the ledger was tilted, the result was a cosmic remainder, one extra grain in a billion. From that remainder came hydrogen and helium. From hydrogen and helium came stars. From stars came carbon and oxygen and iron. From those, the long chemistry of oceans and leaves and lungs. So, we live in the wake of an ancient imbalance, a mistake that became mercy. And if somewhere, someday, a far-off civilization mishandles that mirror fire, the burst we see may look small beside a supernova, but we will know it for what it is: perfect symmetry, reasserting itself for a moment. A brief return to the rule that matter and antimatter obey without sentiment. Then we might look back at our own sky with a steadier gratitude. The universe could have been nothing but light, bright, empty, and brief. Instead, it kept a handful of seeds. They grew into galaxies and into us. Whether our cosmos is alone, or one room in a mansion of worlds, whether the whole is finite or nested without end, we owe our place in it to that sliver of unevenness, an almost imperceptible tilt that let the night exist and the colors of morning. And the human habit of asking why. Some ideas stretch the mind the way night stretches across a quiet sky. They don't demand belief so much as attention invitations to sit with the puzzle of what's real and what it means for us to be here at all. Thought experiments can feel like lullabies for the rational mind. They soothe not by answering, but by widening the room our questions live in. Among the boldest of these is string theory, a proposal that the smallest constituents of reality aren't point-like dots, but tiny vibrating strings. In this view, an electron, a quark, a photon are not different things, but different notes played by the same instrument. Change the vibration, change the particle, change the harmony, change the forces. Gravity and quantum mechanics so often uneasy companions, might be two melodies resolved within a single composition. The world we touch would then be a tapestry woven from vibrations too small to see, but precise enough to build galaxies. And yet, the score is unfinished. One stubborn silence is dark energy, the smooth pressure that makes the universe's expansion accelerate. Many string theoretic constructions struggle to reproduce a universe with dark energy as we observe it at the tiny magnitude we measure. To bridge that gap, some researchers have explored pictures where our universe is like the skin of a bubble, a lower dimensional brain living on the edge of a larger, ever-expanding space. In such scenarios, extra dimensions may lie just beyond our ordinary senses, and the dark energy we measure could be the faint seep of something larger, a pressure from the wider bubble that our local cosmos merely samples. If this were true, our whole sky would be a boundary, splendid, delicate, and partial. It is a striking image. Reality as nested rooms, dimensions stacked like pages. Our familiar physics, the local grammar of one sheet. Whether or not this turns out to be the right map, it reminds us to hold our certainties lightly. Even if we are very small in a structure far grander than we can picture, smallness is not dismissal. Meaning is local and luminous. It happens where we are, between minds and mornings, in the atoms that let us speak at all, which brings us to those atoms, to the quiet promise that matter is never lost, only rearranged. More than 100 billion people have lived and died before us. Where are their atoms now? The law of conservation of matter whispers a simple answer: everywhere. A human body is mostly water, about 60% by mass, with fats, proteins, carbohydrates, salts, and trace minerals composing almost all the rest. Most of those molecules are gathered around oxygen and carbon, with hydrogen weaving the structure together. When a life ends, the water doesn't end with it. Some evaporates into the air, some seeps into soil, some flows to rivers, lakes, and seas. In time, it all joins the water cycle, liquid to vapor to cloud to rain, and back again. Sooner or later, those same H2O molecules find their way into leaves, fruit, bread, breath, and into other people. What was once part of a loved one might cool your skin on a hot day, or tick softly against a window as rain. Plants take that water, add sunlight and carbon dioxide, and make carbohydrates by photosynthesis, breathing out oxygen that we draw in. When you eat the plants, or animals that ate the plants, their carbon, hydrogen, and oxygen become yours, stitched into your tissues via metabolism, then released again as CO2 and H2O when you exhale. It is a slow exchange, a planetary waltz of atoms, from cloud to leaf to lung to sky, from river to root to vein to tear. The same molecules circulate through time, linking strangers, centuries, and species in a single, gentle loop. The story continues in the dark work of microbes. Your body houses trillions of bacterial companions in life, mostly in the gut, kept in balance by your immune system. After death, that balance falls away. Bacteria begin to metabolize the soft tissues, carbohydrates, fats, proteins, in a process that, at the molecular level, mirrors burning. Complex molecules are broken down. Energy is drawn. The end products are largely water and carbon dioxide, with nitrogen compounds like ammonia and sometimes nitrous oxide, N2O. formed by microbial pathways in soil and tissues. N2O is a potent greenhouse gas, roughly 300 times the heat-trapping effect of CO2 over a century. A reminder that our chemistry keeps speaking to the sky, even as we return to it. None of this is morbid if we listen softly. It is a story about continuity. Proteins unweave into amino acids. Fats split into glycerol and fatty acids. Sugars are folded back into the carbon cycle. Minerals, calcium, phosphorus, iron find their way into soil, bone of future creatures, shells, and stone. Some atoms drift to the sea. Some rise into the breath of forests. A rare few, caught in the push of solar wind or the tumble of meteor dust, may even escape into space. Your body is a temporary arrangement. Your atoms are travelers. It is comforting to place this journey beside the cosmic speculations that began our section. If string theory's vision is right, the same strings that vibrate as your oxygen molecule's electrons also sang the early universe into shape. If our cosmos is truly a boundary, a bubble skin on a larger sea, then our atoms are standing waves on that skin, borrowed modes in a resonant hall. Either way, the value of a life does not shrink when the room grows larger. A lullaby is not less beautiful because a symphony surrounds it. We might not yet know why the universe chose quantum notes instead of classical bricks, or why dark energy is so small yet so sure, or whether extra dimensions sit a whisper away. But we do know this: the matter that holds your memories is ancient, handmade in stars, recycled without haste. Calcium in your bones once shone as starlight. Iron in your blood once anchored the heart of a supernova. Carbon in your cells once drifted as invisible air. When your body's organization loosens, those atoms will travel on, joining rain and wheat and song, inheriting new purposes in other lives. So let the thought experiments keep their watch strings vibrating under everything. Bubbles beyond the bubble, dimensions like rooms we haven't opened yet. Let them enlarge the night without emptying it, and at the same time, let the simple cycles be enough. Water rising and falling, carbon turning and returning, oxygen passing from leaf to lung and back again. We are made of ancient travelers. We are mended by their arrivals and made generous by their departures. If there is a lesson folded into these layers, speculative and certain, it might be this: we belong to the world twice. First as a pattern, briefly gathered from atoms, warmth, and will. Then as atoms again, loosened back into circulation, ready for future shapes. Neither place is meaningless. Both are stitched into the same fabric, under the same quiet laws, lit by the same patient stars. When breath has stilled and the body grows quiet, chemistry keeps moving. The first caretakers are the familiar aerobic microbes, but as oxygen thins, a new choir takes the lead. Anaerobic bacteria, comfortable in the dark. They do not burn with oxygen's bright flame. Instead, they work more slowly, rearranging what we were into, what the world can use next. In that hush, tissues soften and yield, and small, pungent messengers slip free: methane, hydrogen sulfide, ammonia molecules with sharp scents and surprisingly potent warming power in the air. They lift, disperse, dilute into sky. The next time a faint, earthy note rides a breeze, you may be breathing a whisper from someone long loved, not in a mystical way, but in the honest arithmetic of atoms finding new homes. Beneath the surface, the ground becomes a ledger. As the body returns to soil, its elements slowly join the mineral commons. For every kilogram of dry mass, roughly 32 grams of nitrogen, 10 grams of phosphorus, 4 grams of potassium, and 1 gram of magnesium seep into the earth, a quiet gift. Roots thread through, tasting this bounty. Microbes broker exchanges. Nearby plants green a little deeper. Flowers bloom brighter, not because of sentiment, but because the chemistry is right. What fed you now feeds the field. Cremation tells the same story at a different tempo, a bright, brief wind instead of a slow rain. In the heat, the familiar elements: hydrogen, carbon, nitrogen, oxygen, sulfur, leave in gaseous form, water vapor, carbon dioxide, nitrogen oxides, sulfur oxides. The room grows warm. The flue carries them skyward, and within hours, what would have taken months has already joined the air. What remains is ash, several kilograms, often close to your birth weight. A circle quietly closed. The ash is mostly calcium phosphate, the long architecture of bone laid bare. It is pale, friable, and ready to take part in soil again. Scattered or buried, those minerals do what minerals do. They enter cycles. A handful, sprinkled beneath a sapling, becomes scaffold for wood and leaf. Powdered bone enriches a garden bed where beans climb and tomatoes swell. The atoms do not remember us, but they continue our intentions: to support, to feed, to build. In time, they travel into grain and fruit, into milk and meat, into the breakfasts of great-grandchildren who will never know your name and yet will carry you forward, cell by cell. Nothing macabre in it, only continuity. The body's last kindness. There are, within us, trace radioactive elements that choose their own clocks. Potassium 40 transmutes by slow nuclear bookkeeping into calcium and argon. Thorium and uranium walk patient decay chains toward lead. These changes happen whether we are here to notice or not, and their products join the same shared pools of rock, soil, and air. Along the way, tiny parcels of helium, born as alpha particles, are made. Helium is noble and light. Earth's gravity can't hold it forever. It slips upward through caves and pores, across night air, out of the sky. Some of it may be herded by the sun's magnetic fields, some stolen by Jupiter's deep well, and some simply drifts into the dark, a soft exhalation to space. Not every atom chooses a short orbit. A thin fraction is swept outward by solar wind, carried on dust, or launched by the rare violence of impacts and volcanoes. They become passengers between worlds. A carbon that once sat in your muscles may someday coldly circle beyond Pluto, or settle into the interstellar medium, that thin, star-spangled fog from which new suns and planets are born. In a few 100 million years, it might burn in a young star's light, or rest in the ice of a comet, or help sketch the backbone of a new living thing on a world where dawn sounds different. There is comfort, if you want it, in the ordinariness of this, the anaerobes that finish what life began, the gases that rise, the minerals that fold into roots, the ashes that turn to food, the isotopes that keep their own slow time, the helium that leaves us singing it is all one motion. Nothing is wasted. The universe is patient and exacting with its matter, and we are part of that care. When the story of a body ends, the story of its atoms doesn't. They continue as rain and stone, as branch and breath, as ribbon of gas slipping past the moon, as dust in a sunbeam crossing a child's room in some other century. We do not hold them, we only host them a while. And when we let them go, they know the way. Stand for a moment at the shoreline of time. Tides keep their rhythm, months turn like patient pages. The sun rises and sets with comforting certainty. Yet beyond this local lullaby, the cosmos is restless. Stars are born by the millions each day, and others dim to silence. Even our sun, in a few billion years, will swell into a red giant, scorch its nearby worlds, shed its shimmering skins, and fade. Against that grand impermanence, a gentler question arrives. Do atoms, the small keepers of all form, endure forever? Part of the answer is already in us. When your life's pattern loosens, your atoms do not vanish. They take new assignments. Rain and root, bread and breath, stone and stardust. Matter is conserved. The ledger balances. So in one sense, atoms outlast us easily. But the deeper question is about intrinsic endurance. Given enough time, do atoms themselves persist unchanged? Or do they, too, bow to time's wider choreography? Begin inside an atom. Its identity is set by the number of protons in its nucleus, the atomic number. 2 protons is always helium. 6 is carbon. 8 is oxygen. Neutrons add weight and nuance. Some counts yield stable nuclei, others wobble. When the balance is off, a nucleus can quietly rearrange itself by emitting a particle or a packet of energy, a process we call radioactive decay. In light nuclei, a neutron may change identity into a proton or vice versa, nudging the atom along the periodic table. In very heavy nuclei, the whole cluster may split or shed pieces to find a calmer configuration. This business is not clockwork. It is probabilistic. We cannot point to a single atom and say exactly when it will transform, but in a collection, we can speak of half-life, the time by which half the atoms will, on average, have decayed. Some half-lives are quick breaths, others are longer than any mountain's memory. Over eons, many unstable isotopes march toward stability, or to such vast half-lives that, for all practical human purposes, they are still. Consider bismuth 209. For a long time, it was thought truly stable. Now we know it undergoes alpha decay. With a half-life so long, it beggars language more than 1 billion times the age of the universe. If you hold a sample today, its change is so slow that across civilizations, continents, and climates, it is effectively constant. At that scale of endurance, forever becomes a word about perspective. But what if we look past nuclei altogether, past the small trades of neutrons and protons, and ask about the foundation stone itself, the proton? Could protons decay? In many grand ideas that seek to weave the forces together, grand unified theories like the Georgi Glashow model protons are not fundamentally protected. They might, on fantastically long timescales, transform, for example, into a positron and a neutral pion, with the pion swiftly becoming 2 gamma-ray photons. Numbers you meet in such models are astonishing. To 10 to the power of 34 years, for a half-life, 100 billion years. That is not a promise, only a possibility. Experiments in deep, dark water detectors have not seen proton decay. They have only placed lower bounds, pushing the minimum lifetime past 10 to the power of 34 years for common channels. The universe may keep this secret a while longer. Between the near and the ultimate lie many scales of change. Electrons can be knocked free and rebound. Atoms can ionize and recombine. Molecules can shuffle bonds. Elements can be forged in stars and scattered in supernova winds. Across these changes, an atom's identity is sturdy when its nucleus is stable. Carbon in your body may become carbon in a leaf, then stone, then air, the same 6-proton core threaded through different stories. Stability at the nuclear level grants an atom a kind of practical immortality measured in continents and star ages. But the universe writes in longer sentences than stars and stones. After the last bright suns have burned the last easy fuel, after galaxies have slowed their feasting and the sky has thinned, the question of ultimate endurance returns. If protons never decay, atoms built from stable nuclei could, in principle, persist for unthinkable spans. Their electrons occasionally stripped by stray radiation and later recaptured, their form shifting but their cores intact. If protons do decay, the ledger still balances mass, becomes energy, fields flutter and fade, but the long, slow dimming of matter would be certain. The universe would coast toward a thin hush of particles and light, not an end exactly, but an exhaustion, even within our present epoch. Decay is not a sentence, it is a path to balance. Unstable isotopes step down to stability, emitting neutrinos, electrons, gamma rays, small notes on their way to rest. The variety of half-lives stitches our world to time. Radiocarbon lets us date the recent past. Uranium and thorium chronometers measure the ages of rocks and planets. Trace isotopes in starlight whisper the histories of stellar furnaces. Atoms are not merely the stuff of things, they are timekeepers. So, do atoms last forever? The most honest answer is layered. For the span of human life, yes, staggeringly so. For the span of civilizations and species, still, yes. The atoms that compose us will remain available, sturdy participants in the water cycle, the carbon cycle, the mineral traffic of soil and sea, for spans that reach past stars, past galaxies, toward the far horizon of cosmic time. The answer depends on physics we have not yet pinned down. If protons are eternal, atoms can be too. If protons are mortal, matter will one day thin. In either case, forever is not a single cliff, but a series of terraces, each wide enough to hold meaning. What to make of our smallness beside such scales? Perhaps this: continuity is not the same as unchanging. The atom in your blood today may once have cooled the skin of an ancient river animal, or drifted as volcanic CO2 through a fern forest, or shone as part of a young star. It may, in some later epoch, rest in a comet's ice or a quiet interstellar cloud awaiting the birth of a new sun. The atom's immortality is a patience with roles. Its death, when it comes, is another kind of participation in the universe's long arithmetic. Between the very small and the very large, we find our scale, a human middle. We wake, work, love, wonder, and sleep in a span where atoms are reliable and stars are steady. We inherit stability enough to build memory and make promises, and instability enough to power skies and stir evolution. To ask if atoms last forever is to ask if there is a final stillness behind all motion. The universe's current answer is gentle and provisional. Not yet and not here. So we set the question down beside us, not solved, just quietly shared like a small lamp left glowing on the bedside table. The world has its long currents, and the little pieces that made us will go on writing them, stitching before to after in patient threads. That is enough for tonight. The room grows dim. Outside, a slow ribbon of starlight slips past the window. Inside, the hum of the day loosens and thins. Inhale and feel the long story move through you. Exhale and let it drift on without your keeping. The names of things fade first, then their edges, then their weight. You don't have to hold any of it now, not the sky's distances, not the ages to come, not even the thought of how long matter lasts. Set it all down. The dark is kind and spacious. When you wake, the current will still be moving. For now, close your eyes, float low and quiet, and let the night carry the rest.